All right, thank you. And thanks for having me, inviting me to this beautiful new campus. If I seem a little loopy, my excuse is that I'm not completely over my jet lag yet, so that's my excuse. Also, that covers any sort of mistakes I make, wrong things I say, and so on. Okay, blanket excuse. So in my lectures, I want to talk about this subject which goes under the name entanglement entropy. So let me just start with the first word. Entanglement is a feature that is ubiquitous in quantum systems. It's one of those things that sharply separates quantum mechanics from classical mechanics, like the superposition principle, the uncertainty principle. It's one of those things that is special to quantum mechanics. And so you can ask, given, for example, a quantum field theory or any quantum system, given any quantum system, you can, some state, you can divide the system into two parts and you can ask how entangled they are. Okay, this is the kind of thing I'm going to be talking about for my lectures. And in particular, asking this kind of question is a very fruitful way of thinking about quantum field theories and also thinking about quantum gravity. Now, quantum field theories have been around almost since quantum mechanics, almost 100 years. And entanglement, the idea of entanglement has also been around almost since the beginning of quantum mechanics. But the idea of asking in a field theory how entangled two parts of the field theory are is a surprisingly recent question to ask on that time scale. So people only first started even asking the question about 25 years ago or so. And really, it's only in the last 10 years that this has become, on its own, a major subject of research with kind of an exponentially increasing amount of activity over the last 10 years or so. And it turns out, so this is sort of the fundamental question people are asking. The activity has been sort of in two fields, although really going in parallel. In condensed matter theory, especially hard condensed matter theory, quantum condensed matter theory, where it turns out to be a very fruitful way of studying many-body systems, strongly interacting many-body systems, and in high-energy theory, and quantum gravity, where it originated in trying to understand black holes and the origin of black hole entropy. And it turns out to be a very useful way of thinking about field theories abstractly and also quantum gravity, okay? So I want to, in my lectures, I kind of want to give some sense of what the main ideas are. I'm not going to attempt in any way to be comprehensive, and I'm also not going to attempt to be particularly careful. Okay, so it's going to be a bit of an overview, just sketching out some of the main ideas. Okay, so my outline. And I'm not sure that these, I'm going to have three sections. I'm not sure how closely they're going to correspond to the three lectures. So first I want to just introduce the basic tools and concepts, some of which we already saw this morning in Apurva's lecture. So what is entanglement and what is the connection between entanglement and entropy? Why are these two words always seem to be stuck to each other? So this will be just in general about quantum systems, but then we want to specialize to field theories. But as a warm-up, I don't want to jump right into quantum field theories. In order to develop some intuition, we're just going to start with simple spin systems, and then work our way up to field theories and quantum field theories, and finally conformal field theories. And I'll try to convince you that thinking about entanglement and quantifying entanglement teaches us about the properties of these field theories. Okay, so throughout these lectures, I'm very much taking the point of view of the physicist who is studying some system and trying to understand what's going on in that system, using a tool from information theory, as opposed to using a tool from information theory to build something or to build a system that does something for us. Okay, so I'm really going to try to use this tool to take apart some system that was given to us, that we found in nature. Okay? And then it turns out that this notion of entanglement entropy becomes particularly interesting and powerful in the context of a certain type of quantum field theory. So we're going to specialize ever more to a certain type of quantum field theory which has a direct connection to gravity. So this is where I'm going to explain this last word in the title, holography. So there's a certain type of field theory called holographic field theories which are directly related to gravity. So first I have to explain what holography is, and then having done that, we'll see the role that entanglement entropy plays in those field theories. Okay. That's what you have to look forward to if you come back. So I guess you've already had a week and a half on information theory. As far as I understand, up until this morning, classical information theory. So I heard the lecturers toss around mutual information and so on, so that's great, so I don't have to cover that stuff. But I do want to just say a few words about the classical case before going on to the quantum case, just to emphasize some things that are different, essentially. Well, some things that are the same and some things that are different. So, of course, we have the Shannon entropy for some probability distribution. So we have some set pi, and then we have its Shannon entropy. Which tells us basically how ignorant we are if this represents our knowledge of which state the system is in. And so in particular, S is 0 if and only if the PIs are all 0 except for one of them, which is some particular which is 1, okay? So in this case, if the system, so I'm always thinking of some classical system which has some bunch of states it could be in, and we don't know which state it's in. This is the probability distribution. So it could be, for example, a Gibbs ensemble at some temperature. And S is basically quantifying how ignorant we are about the state. And if S is 0, then that means we know which state it's in, which means that all observables have definite values in classical mechanics. Now, it's sometimes easy to forget just kind of how magical a quantity like this is. Well, actually, let me go on for a minute, and then I'll come back to that philosophical point I want to make. And so then, of course, if we have a joint system, so let's say with two parts A and its complement, then we have these very useful quantities like, well, let's say, sorry, changing my notation on the fly, always a bad idea. So let's say we have some big system, and then we have parts of it, some A and some B parts of it, then we have the mutual information, which characterizes the amount of correlation. And then we have the conditional entropy. And these are all of these guys are non-negative. And so in particular, that implies that we have this series of inequalities, which means that as a special case, if, let's say, AB is in a definite state, then A is in a definite state. Okay, this is just from the classical point of view, this is kind of obvious. If the full system is in a definite state, then by definition, every part of it is. Okay? Now, one thing I want to emphasize before going to the quantum case is what's incredibly useful about quantities like this is that they're calculable. And so, for example, the Shannon entropy tells you how many bits you need for a maximally compressed coding of the state. Okay? And that means that you don't have to think about how you would do the coding to know how many bits it would take. Okay? All you have to do is calculate this. Similarly, the mutual information tells you the amount of correlation. It's just something you can, if you know the probability distribution, the joint probability distribution, you can just sit down and calculate this. Actually, finding correlations may be very hard. They may be hidden in some complicated, subtle way in the variables in which you're working. So it may actually be very hard to know a priori whether or not there's any correlation between A and B if you just look at these variables. Like if you, for example, if you calculate a correlation function, you have some variable which depends on the state of A, some variable which depends on the state of B. You say, okay, I'm going to calculate a correlation function. The expectation value of the A variable times the B variable minus the product of their expectation values, you may get 0. Maybe that's because they're uncorrelated, or maybe it's because you chose the wrong variables. But if you compute this and you find that it's non-zero, you know that they're correlated. And if you find that it's 0, you know that they are uncorrelated. okay? So these are actually sort of rather remarkable quantities, and what we're going to be, always interested in, we're not going to be that interested in sort of abstractly defined information theoretic quantities, which sort of abound, especially in quantum information theory, where you have all kinds of quantities that are expressed as, the maximum number of qubits, or let's say the minimum number of qubits required to carry out such and such a protocol. And that's the definition of the quantity. And then it's up to you to search over all protocols, if you want to compute this, to know what is the value of this quantity. So quantities like that, are not so useful because, of course, we'll never actually be able to, for a given physical system, figure out the optimal protocol for doing something, for, let's say, extracting bell pairs or something from some part of a system, okay? But quantities like these are great, okay? Assuming we can compute entropies, okay? So that's what we're interested in, is actually calculable quantities that tell us something about the entanglement and the correlations in our system, okay? Okay, in the quantum case, and here, I guess, Fernando, his lecture is going to be a proper introduction to quantum information theory. So what I'm going to tell you is not a proper introduction to quantum field theory. I'm just going to emphasize a few points and do a few definitions and repeat some of the stuff that Apurva already covered. So, I mean, the first key difference is that whereas in classical mechanics, we can make a clean separation between the notion of the state of the system and the notion of our knowledge of the state of the system. In quantum mechanics, there is no such clean separation, okay? So when I use the word state, I don't necessarily mean the actual state. I just mean whatever our description of the state is. What is a description of the state in quantum mechanics? It's a density matrix. Okay, which is, I assume everyone is more or less familiar with this. It's a positive permission operator with trace 1. And because it's Hermitian, we can diagonalize it, and in its eigenbasis, it looks just like a probability distribution, like a regular classical probability distribution. Where these are its eigenvalues. In other words, they're non-negative, they sum to 1, and so we can go ahead and compute the Shannon entropy of this, of its eigenvalues, as if it were a classical probability distribution. Which we can also write in operator form as trace rho log rho. And I should say that, of course, the connection between the density matrix and the observables is that the expectation value of any observable in the state rho is trace of the product of those operators. So, again, we have a similar statement to this one, that if somebody gives you a row and you compute this and you find that it's 0, then you know for sure that one of the rho sub I is 1 and all the rest are 0, which means that rho is a projector onto some state, it has this form. And then we say the state is pure. Otherwise, so. Otherwise, it's mixed. Okay, now in the case, now here's the difference though. Let's say the state is pure. Does it follow that, as in the classical case, that all the observables have definite values? Well, because we're doing quantum mechanics and we have the uncertainty principle, it does not. So this part fails. Okay? So all we have is some observables. In other words, those that pick out this particular state have definite values. But of course, even in the mixed case, some observables have definite values. So the question of whether some observables have definite values in no way separates the pure case from the mixed case. Okay? So here the uncertainty principle is actually throwing a monkey wrench into our notions of how definite the state is. This is as definite as the state can be, but because it's quantum mechanics, it's still not really all that definite. Okay? Okay, so now we want to talk about subsystems. And so I'll call a subsystem A. And there's always a basis. Well, for my purposes, actually, what I'm going to say next is kind of arguable in interesting cases, but I'm just going to gloss over the subtlety. And for our purposes, we're just going to assume that there's always a basis of factorized states. Okay? So we have some basis of states that look like this, where this is a state of A, and this is a state of its complement. Okay, for example, let's say we have spin a half, so very familiar, times spin a half, and we have a basis that looks like this. Okay, but of course, by the superposition principle, not all states, not all pure states. So, yeah. Actually, on this slide, state means pure state. So, of course, famously, we have states like this. Spin singlet state, which is up, down, minus, down, up, and these are the entangled ones. Okay, so that's presumably familiar to everyone. But it's a little bit tricky because let's say I write down a state like this, and I'm going to abbreviate my notation by merging these kets. So here's a state. And here's another one, the same, but with a minus sign here. They look rather similar, okay? But as it turns out, and it's not hard to convince yourself this is true, this one factorizes, and this one doesn't. This is entangled, this is not entangled. Now, we're very interested in the question of whether some state on the joint system is entangled or not, right? So we don't want to have to just do it by inspection every single time. And we also want some way of quantifying how entangled they are. Okay, some machine. Okay, preferably, you know, the most automatic kind of machine we can find that answers this question. Okay, so that's going to be our aim. Now, to study this, let us consider the question of what is the marginal. So when we had a classical probability distribution on some joint system, on two variables, we have the marginal distribution, which is if you just don't look at one of the variables, okay, the probability distribution. So we can ask the same question here. If I just don't look at A complement, then what is my state for the purposes of observables on A, okay? So we can use, So first of all, what does it mean in quantum mechanics for an observable only to be on A? It means that on A complement it acts as the identity operator. So we write something like this: O is OA tensor identity on A complement. And that means that its matrix elements in this basis look like this, and hopefully the notation won't get too nasty. So if I now just ask, well, okay, for an operator of this form, for an observable of this form, what is the expectation value? Is there something special we can say about it? Well, when you write it out, whoops, sorry. You get this. Where you separate the sum, we have to do the sum on the A indices and the A bar indices. But the sum on the A bar indices is easy because the operator is just the identity on the A bar indices. So in fact, this can be written like this. Trace just on A of OA. So where this thing, by definition, is what I call rho A. Well, these are the matrix elements of rho A. So this is the marginal or reduced density matrix. So it's a state just on A. This is an operator which only acts on the A Hilbert space. And it answers the question, what is the expectation value for any observable which also acts only on the Hilbert space? Okay, so it's the effective state for an observer who only has access to A. Okay, for that observer, all questions are answered by this density matrix. They have no way of knowing what rho is. They can only, by doing any experiments they want, know what rho sub A is. Okay? So, for example, okay. Well, maybe I can do it over here. Yeah, let's just do it right here. If I take this spin singlet state, and I take the first spin to be A and the second spin to be A complement, when I do the trace, oh, and in fact, let me write a different formula for this. Trace on B of rho. Oops. I'll rewrite these important formulas. Let me write them here. I guess some of the observers didn't have access to this part of the system. Okay, that was the punchline. Can I write down here? Is this okay? All right. Okay, so if we do the trace, so first of all, of course, rho, in this case, rho in this pure state looks like this. And now if I do the trace on the A bar, you get nothing from terms that have this ket, but let's say spin down for the ket on A bar, but spin up for the bra. Those don't contribute to the state, to the trace, and so you just end up with this state. In other words, you get the term from this squared, that contributes this term, and then the term from this squared, which contributes this term, and you get no cross terms in this particular state. Okay, so guess what? If I now compute the entropy, the von Neumann entropy, which I should have named here, the von Neumann entropy of my state on the full system was 0 because it's in a definite state. But the von Neumann entropy now, this is actually a maximally mixed state on this subsystem. 50% chance you find spin up, 50% chance you find spin down. And so when you calculate S of A, you get log 2. So you got entropy out of thin air, okay? There was no ignorance about the state of the system. You knew exactly which state the system was in. You knew as much as anyone could possibly know. Okay, quantum mechanics doesn't allow you to know more about the state of the system than you do for this state. And yet, when you, simply by covering up half of your system, you suddenly gain some ignorance. So you violated this. See, this was 0, this is non-zero. You violated this inequality. So you actually have a negative conditional entropy. You're more ignorant about a subsystem than the full system. And the reason that this can happen, it seems logically impossible, but the reason is that this was already violated in quantum mechanics. So it was already true by the uncertainty principle that there are lots of observables, even for this pure state, which did not have definite values. Okay? And there's only very few observables which do have definite values, the ones that are specially tailored to this particular basis. And it just so happens that none of those observables are located in A alone. All of the observables that have definite values actually require you to do simultaneous measurements on A and B, A and A complement. Okay? So when it happens that any observable you might do that tells you that you're in a pure state, that has a definite value, is always requires a joint measurement of your two subsystems, then you're in an entangled state. Because all the measurements done on just one subsystem will never give a definite value, and then you have a mixed state effectively for that subsystem. Okay? So there's a close connection actually between entanglement and the uncertainty principle. These two, very famous properties of quantum mechanics are very closely related to each other. And so we've learned that the von Neumann entropy of, which is just this, of the subsystem is a good diagnostic of entanglement, at least in the case where the full system is pure. Okay? In the case where the full system is pure, if you compute this, and again, the point being this is calculable, you will learn whether or not the two subsystems are entangled with each other. And that's why it has the name entanglement entropy. So again, you can't separate the state of the system from our knowledge of the state of the system. I just want to re-emphasize that. Okay, that clean separation that exists in classical mechanics just doesn't apply to quantum mechanics. So any subsystem which is not entangled, so in fact, let me I haven't, just hold on one second. Let me justify this statement I just made. So let's consider the case that you happen to have a factorized state. Okay, let's say your state of the full system happens to factorize. An important special case. Then what does rho sub A look like? Well, then rho sub A just looks like this. And you get 0 for the entanglement entropy. So, and in fact, the arrows go this way for some phi A, and then they go this way. Okay. Okay, now a warning about terminology. Okay, people who are serious about quantum information theory only use the term entanglement entropy when the full system is pure. When the full system is pure, the entropy of a subsystem comes from entanglement, so it deserves the name entanglement entropy. However, people who are not serious about quantum information theory, who do it as amateurs, very sloppily use the term for this quantity, regardless of whether the full system is pure. It's sad but true. So you have to be careful when people talk about entanglement entropy. They may be talking about something which has nothing to do with entanglement. This makes people who are serious about quantum information theory want to cry. But it does happen, and it is the standard terminology in my field, which is high energy theory. So you can have the following situation, that the full, the state of the full system looks like this. Where this one happens to be mixed, which implies that S of A is positive. And yet manifestly, there is not only no entanglement, there's no correlation of any form between A and A complement. For example, let's say you have two decoupled systems. The Hamiltonian is just the sum of the Hamiltonian on A and the Hamiltonian A bar. You put the thing at some finite temperature, well, they're still not correlated. And the density matrix is just the Gibbs ensemble on A, tensor product of the Gibbs ensemble on A bar. Nothing could be more boring. And it has an entropy, whatever the entropy of A is, the existence of A bar is totally irrelevant. And yet, people would still call this quote-unquote entanglement entropy. Okay? So the term entanglement entropy is used, what it should be called is just subsystem entropy. Okay? Whether the origin of that entropy is entanglement or it's simply mixedness of the full system. Okay? Okay. So there's a big difference between entanglement and classical correlation. So this is an example of an entangled state. So what's an example of an unentangled but correlated state on the same system? So when you compute, I mean, I sort of, my notation cheated a little bit, but if you compute the reduced density matrix for this state, you will indeed find what I called rho sub A, which I just assumed was mixed for the purposes of this illustration, this cautionary tale, and that's why it was, I mean, I'm just assuming that it's mixed in order to emphasize. Yeah. Right, so it could have entanglement entropy in the sense of this, but it would not have entanglement, right, between A and A complement.
It could have entanglement within A.
Oh, it could have entanglement within A. That's right, yeah. So this state is entangled. By the way, in my lecture, I'm always, by the state 0, because I'm going to be using it so often, I always mean this state. Whereas this state in fact, let me do this case. So this is a mixed state. And in this mixed state, if you measure the first spin and you find it spin up, you know that the second spin is spin down, which is also true in this state. So in both states, you have a correlation between the two spins. They're always perfectly anti-correlated. So as far as those measurements are concerned, which are only done in the spin z basis, these look the same. But, and where you're, yeah. But of course, these are very different states. In particular, this is a pure state and this is mixed. And this is simply an example of classical correlation. Okay? And in particular, well, so in a second, we're going to calculate the mutual information for these two cases. But first, I want to point out that by doing another case, the fragility of entanglement, because, see, it's kind of paradoxical. On the one hand, entanglement is ubiquitous in the sense that it's kind of hard to avoid. Like if you pick a random state from the Hilbert space of some joint system, of course it's going to be entangled pretty much all of the time. You would have to work pretty hard to find a state that's not entangled. The unentangled states are much rarer. On the other hand, because entanglement depends on superposition, and superposition is fragile and can easily be decohered. This is what makes it hard to build a quantum computer. Quantum computers, for their power, depend on very delicately arranged superpositions of states, but superpositions tend to decohere by interactions with their environment. And when the superpositions decohere, the entanglement goes away, or rather, it gets converted to classical correlation. So let me give an example. We consider the GHZ state on 3 systems, which is this one. So 3 perfectly correlated spins, which we call A, B, and C. Okay. Now, if I just factorize this, if I write it like this, then I hope you'll agree with me. So I've separated A from BC. I hope you'll agree with me that A is entangled with BC. But let me ask a different question, which is whether A is entangled with B. It might seem obvious, like if we're talking about classical correlation, if A is entangled with BC, then A can certainly be if A is correlated with BC, then it's certainly possible that A is correlated just with B. It doesn't have to be. It could be that A is correlated with just with C. But it's going to have to be correlated with some part of BC in some way. So, but let's look at this system and let's ask whether whether that holds for entanglement, whether A is entangled with B. So if you're going to ask whether A is entangled with B, you're now asking a question not about the full ABC system, but only about the AB system. To answer that question, I need to know what the state of the AB system is. So I need to compute row AB, right? I have row ABC, which is this pure state. But what is row AB? Well, I need to trace over C. And when I trace over C, it's the same game as we did here, where the cross terms don't contribute to the trace on C, and I get this state. Well, actually, I already wrote it up above, but I'll write it again. Well, I wrote something similar up above, I guess. Voila. There's no entanglement between A and B. Okay? So tracing over C decohered the superposition, made it into a mixture, And the reason that happened is because AB was entangled with C. So when I traced over C, I decohered that superposition, and I made it into a mixture on AB, and that mixture has no entanglement. So in fact, in this state, if you ask whether A is entangled with B, the answer is no. A is not entangled with B. A is just correlated with B. Okay? So the entanglement very much depends, whereas if, let's say I had a classically correlated system of 3 particles that were either, 50% chance they're all spin up, 50% chance they're all spin down. It doesn't matter which parts, the amount of correlation between A and B, between B and C, between A and BC, it's all the same. They all have the same amount of correlation. It doesn't matter if you cover up C, that doesn't change what's going on with A and B. But with entanglement, it very much does. Okay? Now, let me. Oh, there was one other thing I wanted to say before talking about mutual information, which is that you can easily show that if rho is pure, then S of A equals S of A bar. Which is useful to know. It goes beyond that, actually. The full spectrum of rho sub A is the same as the full spectrum of rho sub A bar, except for possible adding a bunch of zeros on one side or the other. But the non-zero part of the spectra are the same. Okay. So we can define the mutual information in the same way as in the classical case. And let's just see a couple examples. Well, if the full thing is pure, then this is 0. If the AB system is pure, then this is 0 and this equals this. So you could just get twice the entanglement entropy. Okay? So for example, if rho AB is this, then the mutual information is 2 log 2. On the other hand, as we know from the classical case, like here, for example, or here, in the case of classical correlation, if you compute these terms, well, again, A is 50% spin up, 50% spin down, that's log 2. Same with B, same with AB. So you get log 2 plus log 2 minus log 2, so you just get log 2. So in this case, and in this case, the mutual information is just log 2. So maximally entangled, so basically entanglement is like worth double by this measure classical correlation. Maximally entangled pair of qubits, 2 log 2, maximally correlated pair of bits, log 2. Okay? Now, you might be a little bit concerned given that properties that are familiar from classical information theory don't hold. In particular, whereas the conditional entropy is non-negative, in classical information theory, we've been seeing all over the board that that's not true in the quantum case. The conditional entropy can be negative. So does this mean anything goes and anything can do anything, the mutual information can be negative? No. So this is still a very useful quantity, and actually the conditional entropy, even though it can be negative, is also a very useful quantity, but some things that are familiar from the classical case still hold here. So one is subadditivity. And with equality holding if and only if rho is a tensor product, rho AB. Okay, so this is a great, again, the fact that this tells you how much correlation there is still holds. If you calculate this and you get 0, you know there's no correlation. If you get something non-zero, you have some correlation or some entanglement, or both correlation and entanglement. You can be sure that it's only entanglement if this is pure, if rho AB is pure. But if rho AB is mixed, the situation is very murky. This quantity does not distinguish, in that case, between entanglement and correlation, in the sense that, I mean, of course, if you know more about your system, you can tell the difference. Like, the value is different in these two cases. But you can't tell the difference between, let's say, 2 pairs of classically correlated bits and 1 entangled pair of qubits if all you have is the mutual information. Okay? So this combines entanglement and you could ask, well, how do I know whether there's entanglement or not? Like, let's say I go ahead and calculate this. I find it's non-zero. My full system is mixed. So I can't be sure there's entanglement. What do I do now if I want to know whether there's entanglement? And that is actually an open problem. That is very, very hard. There are some things you can calculate that will prove there is entanglement, but there's nothing known that you can calculate easily that will guarantee you that there's no entanglement. So actually identifying unentangled states, or states that have only classical correlation, is an open problem. Okay? And the other thing that's hard, which is closely related, is if you want to quantify how much entanglement there is, put a number to it, then it turns out there isn't a single number or anything you can straightforwardly calculate that quantifies the amount of entanglement. It starts to depend on the details of the question you're asking. So you can ask a question like, by some protocol, how many bell pairs, a bell pair is a maximally entangled pair of qubits, how many bell pairs can I extract from the AB system? You can ask a different question, which is, how many bell pairs would I need to use to recreate this state? And you get, these are different quantities, and there's actually a long list of other quantities you could use to answer the question, how much entanglement is there? And those quantities, they're of this form, like, what is the optimal protocol? How many bell pairs do I need in an optimal protocol for doing such and such? In other words, there's no way you could ever calculate them. You just have to search over all protocols. Okay, so from our point of view, they're kind of not so useful. Okay? They're very useful in studying quantum computation, quantum information theory, and they're useful because you can prove theorems about them, but they're not quantities which you ever sit down and calculate in a given actual system. Okay, so this is a very important property. And another property which is also true in classical information theory, which should make you feel a little bit better, is this one, that tracing out part of your system can never increase the amount of correlation. Okay, so this is equivalent to this inequality, just by unwrapping the definitions. And this goes by the name strong subadditivity. And we already saw an example of that. So, I mean, there's a couple of reasons why the left-hand side might be larger than the right-hand side. One is that maybe C was correlated with A or entangled with A, in which case when you trace over C, you lose that. That would contribute only to the left-hand side and not the right-hand side. Another possibility is that by tracing over C, you decohere some of the entanglement, which cuts you down in the mutual information by a factor of 2. So we saw that. So this is an example of that, where the GHZ state, by virtue of this, has a mutual information 2 log 2, but A and B only log 2. And you can actually, similarly to this case, you can make a precise statement about when this is saturated, but I don't want to go into that. You can characterize the states where it's saturated. And it's basically very similar to the classical case. Okay, that was what I wanted to say about entanglement in general, entanglement and entropy. So let's take a pause. Any questions before I move on? Mm-hmm.
You're saying there's no way to define SFA which will take the entropy because of
Right, you would want some way, exactly. So having computed S of A, you would somehow want to subtract out the part which is due to the fact that the full system was mixed. But that's not actually, I mean, that in itself is not well defined. Or it doesn't have any other definition, yeah. Like I said, there are quantities you can compute, so again, calculable quantities, which if they come out non-zero guarantee that there is some entanglement. But the other way around does not exist. Okay, on to part 2. Okay, so I'm going to presume that, like me, you are interested in quantum field theories. Okay? I'm not going to justify why we care about quantum field theories, but we care very deeply about quantum field theories. Okay? They describe many types of systems, from condensed matter, nuclear, high energy, cosmology, all kinds of physics, okay? And we need desperately tools to understand quantum field theories, to characterize them. And an example of the kind of question you might ask, just one example, but the type of thing that they problem that they encounter in condensed matter physics is the following. You have some spin system or some description of a many-body system which you have reason to believe is described at long distances by some continuum quantum field theory. But what quantum field theory? Can you say something about which one it is? Can you write down a Lagrangian? Can you say what the fields are? This is very hard, okay? So if there's anything that you can compute, let's say you can efficiently, simulate this spin system on a computer, up to some lattice size or whatever. Is there something you can compute that would then give you information about what that continuum quantum field theory description might be? Okay. One thing, of course, is you look at the spectrum of excitations. You look at correlation functions, so these sorts of things. Maybe you try to compute some scattering amplitude. So here, it seems like one very reasonable thing you might do is to ask how entangled are two parts of your system, okay? And also, you might just be curious, because now that we have this point of view on quantum systems, given that quantum field theories are quantum systems, you might just want to know what is their entanglement structure? Okay, how entangled are different parts? Now, I just want to clarify one thing. When you're talking about correlation functions, you might talk about, let's say, how correlated this field at this point is with this field at this point. And then how does that vary with distance and stuff like that. You shouldn't ask, when you're talking about entanglement or entanglement entropies, how entangled is the field at this point with the field at this point? Because we already saw that if you just look at, if you call this A and this B, and you trace over everything but A and B, you're not going to get any entanglement. You're going to decohere. I mean, they might be correlated, but by the time you're done tracing over everything else, you're probably going to decohere whatever entanglement there might be. So this is the wrong question. Okay, so you don't ask about entanglement between points in a quantum field theory. It's the opposite point of view from the point of view you take when you calculate correlation functions. Instead, you take regions, okay? So we can ask, so if we have some field theory and we pick some region A, we can ask how entangled, and maybe the full system is in its ground state, for example. So this is the kind of question we want to ask, okay? And in particular, and of course there are different things to compute, but I'm keeping it simple, so in these lectures, I'm just going to compute entanglement entropies. There are actually other quantities which you can use to characterize different aspects of the entanglement, especially when you start talking about multiple regions, like I have A and B and so on. But we're just going to compute entanglement entries, mutual information, stuff like that, okay? And if we do that, if we compute S of A, we're going to find that it depends on, of course, whatever parameters our theory depends on. It's going to depend on the state. Like, is the full thing in the vacuum or in some one particle excited state or what? Okay, that's going to change S of A. Or, for example, the full system could be in a thermal state. And of course, the shape and size of A. So actually, it's not one quantity, but even fixing the theory and fixing the state, it's going to depend on how we choose this region A. So there's going to be a lot of information in there. If we can compute it for an arbitrary region, which is probably too much to ask for, but if you just fantasize that you can compute it for an arbitrary region, that would contain an enormous amount of information about the state. Okay? And then what we'll see actually immediately is that it also depends on something else that we don't want, which is not really part of the theory, but it enters, which is you need to regulate the theory, and it depends on the cutoff. So this is kind of a bad dependence, something we want to get rid of. Okay, and we can also consider the mutual information. Let's say we have two regions. To learn about correlations. Okay, so just to build some intuition, before we do field theories, we're just going to do some very crude estimates of what kind of thing we might expect by considering some very simple spin system, where I'm assuming that the spin system is local. It has a local Hamiltonian, and then I'm just going to make the leap to assuming that it has mostly local entanglement. So you could think of it as, so let's say I have some lattice. I'm not really going to justify this. I'm just get a feel for what kinds of things we might expect. And actually carefully justifying this is the kind of thing that Fernando does, and it's you know, it's a real serious business. So let's say we have some spin system with spins on the lattice sites. And let's say, I mean, it may have some complicated entanglement structure, but you might expect if the Hamiltonian is local, so if the Hamiltonian involves some nearest neighbor interactions and you're looking at the ground state, that the ground state might look something like pairs of, you know, singlets in some way. I should have used a different color. I've been terrible about color. Gosh. So let's just take the simplest case where we have these pairs of singlets. And then let's pick our region. And you can also have, I don't know, well, so let's pick our region in some way, so some set of the spins. And you can see that essentially the entropy is going to be basically given by counting the number of links you've broken. Okay? So, so here we have some okay, to say the same thing again. Okay, and what is this, what is the number of bonds that you've cut? Well, it's basically the area or length of the boundary. So this boundary dA is called the entangling surface. Divided by the lattice spacing to the appropriate power. Okay, so sigma is the area or length or volume, depending on the dimension you're in, of dA, the entangling surface. I'll always use sigma for that. This is the number of spatial dimensions. So I'm assuming that the full system is pure. It's in its ground state. Okay? And so I just have bipartite entanglement between A and its complement. So this is A. Rest is its complement. So there's only entanglement. Okay? Anything I find for S of A is just due to entanglement. So now I can properly use the term entanglement entropy. Okay? Okay, so we get this estimate. And the first question I want to ask, so we learned that it's divergent. It's UV divergent in the sense that if I take epsilon to 0, if I take my cutoff away, my S of A goes to infinity. Okay, I mean that, we're very used to, when you compute anything in quantum field theory the first time around, there's always some ultraviolet divergence, some loop correction or whatever, then you have to renormalize, and so on. So no big deal that, you compute something in quantum field theory, you get an ultraviolet divergence, okay? But we will have to deal with it. And you could ask, well, the same question you should ask whenever you see a new quantity, is it a lot or a little? Well, on the one hand, it's a lot because it's ultraviolet divergent. On the other hand, if you think about it, it's actually a little, because how big could it have been? Well, the dimensionality of the Hilbert space for A, whose log is the maximum entanglement entropy you can get, is the exponential of the number of lattice sites inside, which is the volume of A. So this is, I've run out of room. Okay. Much smaller than log dimensionality of the A Hilbert space, which is basically the volume of A over epsilon to the D. One more power of epsilon, a volume divergence. So what I'm saying is that if you look at the ground state of a typical local Hamiltonian, actually in some sense it's highly unentangled. It's much less entangled than a random state you might pick from the Hilbert space. Okay, so ground states are actually highly unentangled because their entanglement is mostly an area phenomenon as opposed to a volume phenomenon. And this actually is the origin of some powerful techniques, variational techniques, where you put that in as an ingredient in your variational ansatz. You say, well, I don't have to think about crazy states where I have some kind of volume proportional entanglement because I know my ground state doesn't look like that. So you can actually reduce your search space enormously by just assuming that you only have an area law entanglement. Okay, I didn't actually, so this logic would pretty much go through for any kind of reasonable state. So if you have, some finite number of excitations, a state that looks reasonable in the continuum limit will also have the same divergent structure. Yeah. Yeah, yeah. Or that you mostly have correlations near the surface. So what I want to do next is actually slightly improve on this estimate, which was very crude and just gave us the leading term.
Does entanglement entropy or entanglement entropy define the dimensionality of your system given a state? When computing entanglement entropy, can you use that to get the dimensionality? So is it exactly the same as the statement of locality?
I think it's true. It's a good question. So let me rephrase the question in a way that might not be equivalent, but if you, let's say I believe the following, okay. The following statement is lore and is believed to be true. If you find a higher power of epsilon, in other words, a worse divergence than this in your spin system, then your spin system is not described by a local quantum field theory at long distances. It does not go over to being a local quantum field theory continuum limit. Trying to prove something like that rigorously, I mean, that's the sort of thing that people like Fernando prove statements rigorously that go in that direction.
Suppose I do last spin transformation.
Mm-hmm. Yeah. Yeah, so indeed, so the next thing I was going to do is to point out that, of course, there are the fluctuations. So essentially, when you're talking about a spin singlet, let's say, you're talking about a fluctuation, a correlated fluctuation. That's what an entangled state is. So some quantum fluctuation which is not localized just on one spin, but let's say on two neighboring ones. But of course, there are fluctuations on different length scales. So there are, in a quantum field theory, you have modes, and the vacuum, let's say of a free quantum field theory even, each mode is in the ground state of harmonic oscillator, and it has some 0-point motion. And so there are these correlated fluctuations on different length scales. And another way to say that is that you can do block spins, and you can see entanglement at the level of the blocked spins, okay, as opposed to at the level of the original ones. And these also contribute, okay? So that's how we're going to refine our estimate a little bit, slightly better estimate. Still pretty crude. Maybe I'll leave it, well, probably leave it at this. Okay, so let's say this is my dA. So I just want to zoom in. Forget the large scale structure of dA. I just want to, let's say this is A bar, some boundary, and then I have blocks of spins that are correlated on different length scales. Okay. So quantum fluctuations So then a very naive estimate would look like this. Well, first, so a given length scale would contribute, well, I mean, how many blocks are there? Well, it's sigma over L to the d minus 1. Right, that's the number of blocks of a size L that get cut by dA. So then you get this, S of A. So we're going to integrate, let's integrate with respect to the logarithm of L, d log L. We want something dimensionless, okay, d log L, of this, sigma over L to the d minus 1. But L, let's say, goes only from the cutoff, that's the smallest L would be, up to the correlation length. Past that, the blocks are not fluctuating, okay? Up to the correlation length, so this, if the system has a correlation length. And I'm assuming here that A is much larger than the correlation length. So we're going for a picture, so imagine it slightly differently so you see what I'm trying to do here. Where once you zoom out, so here's A, and this is the continuum picture, and there's some very small length scale epsilon defining the lattice, much smaller than A. And what I'm interested in now is that also the correlation length, C, is also smaller than A. So there's a range of length scales that are contributing to the entanglement entropy. Okay? Okay, so you do the calculation, and you get our divergent term that we had before. And you get this other term. Okay, so what I want to say now, not that this is a great estimate, and of course there's all kinds of coefficients and stuff. Yeah.
So what happens?
Oh yeah, so if C goes to infinity, holding A fixed, then of course this is garbage. Okay, because I'm only focusing on some, you know, I'm assuming that, again, I'm assuming that A is much larger than C. So I haven't done a critical limit here, okay, for the purposes of this estimate. We're going to do critical systems, okay? Yeah?
Why is log L the right name?
Oh, well, you know, when you do block spins, you do like factor of 2 each time or whatever. So it kind of makes sense. The other thing is I needed to integrate with respect to something dimensional. This is dimensionless. This is dimensionless. So I needed this to be dimensionless. But of course, you know, I could have put, and I probably should have put, some function, some dimensionless function of the dimensionless ratio L over C here. You know, I mean, there's, you know, but the point I'm getting at is that this estimate, as crude as it is, shows that there's hope. This is the point I wanted to make with this estimate. Why? This term is well defined in the continuum limit. Okay? So if I take epsilon to 0, holding C fixed, okay? Because I'm aiming at some particular continuum field theory which has some correlation length, C. This is blowing up, but this is not. And so if I can extract this term, then I have some quantity which characterizes the actual continuum quantum field theory. Okay? Now, I'll just say one last thing. Of course, a better estimate includes all kinds of terms. You have all different powers, sigma over, let's say, epsilon to the d minus 2 times xi, sigma over epsilon to the d minus 3, xi squared, etc. And you have log terms, you know, depending on the dimensionality. You have terms that depend logarithmically on epsilon. It turns out that these terms appear when d is odd. They don't appear when d is even. But the leading term, which is independent of epsilon, characterizes the actual continuum quantum field theory. Okay? Plus, there's all the terms here. I've just made this assumption, so I've basically thrown away anything that that's not just proportional to sigma. But of course, there can be terms that depend on the curvature of dA, so that get to the geometry, the shape of A as opposed to just its size, and so on. So there's lots more information in the entropy, if you can compute it, which characterizes the continuum quantum field theory. So what we're going to do next time is I'm going to stop BSing around with these crude estimates, and I'm going to tell you about a specific spin system where I can actually calculate before your very eyes S of A exactly, and we're going to see how you can extract useful information from the entropy. Okay? Okay. Any questions? Yes?
So I would have thought that all of these issues you could solve by separating it to A and B before you started with lectures. Then you wouldn't worry about area confusion if they're separated. I'm starting to understand why, but I don't know.
No, so, okay. In fact, if I hadn't been in a rush, I would have actually said that also. So the name of the game is not just computing S of A or S of AB or whatever, but from that doing some renormalization where we extract the epsilon independent stuff. And there's various ways to do that. One way is to look carefully at the size dependence. For example, take derivatives with respect to the size. Take enough derivatives that the epsilon dependence gets lost. Another way is what you said. You look at the mutual information between separated regions, and then anything which is any divergence which lives just on the boundary cancels, and that gives you something which characterizes the quantum field theory.
Somehow you were saying that this is going to be dominated by other non-entanglement correlations?
Right. So if I do that, I haven't necessarily learned how much entanglement there is between A and B. That's a much harder question. But I've still potentially learned something interesting about the field theory. Okay, so as far as I'm concerned at this point, I just want to learn something about the field theory, and then maybe later I want to learn how much entanglement is there between different regions and stuff like that. But my first goal is just to write down quantities that do not depend on the particular lattice regularization that actually characterize the continuum quantum field theory. And the mutual information passes that test. As long as it's local, right, then, the same general thing is going to go through. Yeah, it doesn't matter if it was like sets of 3 that are entangled, it would still end up the same. Yeah, I didn't mean nearest neighbor necessarily per se.